Hello everyone, and welcome to our virtual presentation. My name is Jonathan Kim, and I'm here to present our paper, SymbioLCD, Ensemble-based Loop Closure Detection using CNN-extracted objects and visual bag of words. Our presentation is organized into 5 main sections. First, introduction to show challenge, what we propose, and our contributions. Second, related work to show what's out there in our field of research. Then we move on to methods, showing overview and details of each component. Fourth, we show experiments to show evaluations against current state-of-the-art and ablation studies. Finally, conclusion and future work. Simultaneous localization and mapping has been widely used in the field of robotics for simultaneously building a 3D map and finding its localization. Since Visual SLAM relies on visual features alone, it continuously accumulates small drift in its localization, and an accumulation of this small drift can cause a large drift by the end of its trajectory. Loop closure detection is the process of detecting whether a device has returned to a previously visited location, and it's an essential tool of Visual SLAM to minimize drift in its localization. Monocular SLAM suffers relatively larger drift compared to stereo SLAM, which makes the loop closure quite crucial for monocular SLAM. Loop closure detection can be laborious, since it's difficult to know if the features that were observed currently are the same features it observed when it started tracking. Typically, a visual bag of words is used to detect loop closure, and it compares the local image features against a set of features that are stored in the dictionary. It is robust against partial occlusions and viewpoint changes. However, it cannot perceive the semantics or spatial relationships between feature points. CNN object extraction can address those issues by providing semantic labels of each object in the scene and spatial relationships between objects to aid loop closure. However, previous work has mainly focused on replacing visual bag of words with CNN-derived features. We propose SymbioLCD, an ensemble-based loop closure detection system that utilizes both CNN-extracted objects and visual bag of word features for robust LCD candidate prediction. When used in tandem, the added elements of object semantics and spatial awareness creates robust and symbiotic loop closure detection system. Our contributions are as follows. An ensemble-based loop closure detection system that uses both CNN-extracted objects and visual bag of word features symbiotically to create a robust and complementary loop closure detection system. A scale-invariant semantic matching algorithms, a Hausdorff distance with temporal constraints, early detection of loop closure candidates utilizing both spatial and semantic information, and lastly, 3D datasets representing normal household areas with common objects with varying trajectories. There are many existing work in feature descriptors and visual bag of words. Indirect SLAM reduces an image into a sparse set of key points, which are matched using feature descriptors such as SIFT and ORB. Two most popular visual bag of words based approaches are dBoW and FatMap. dBoW uses a tree structures dictionary that are trained over a large dataset, whereas FatMap uses a Chow-Liu tree to learn a generative model of appearances. There has been significant interest in utilizing CNN-derived features instead of using feature descriptors in SLAM, by engaging object detection algorithms like MassCastCNN to extract objects from a scene, and ConvNet features which uses features from higher layers of ConvNet hierarchy to encode semantic information about a scene. In machine learning, ensemble methods use multiple trained models to obtain better predictive performances. One good example is random forest, and it uses a combination of tree predictors where each tree uses input vectors that are sampled independently. Because loop closure is a component that exists within SLAM framework, we created SymbioSLAM as the framework for incorporating the SymbioLCD component. The SymbioSLAM framework is created using DynaSLAM as its base because it incorporates vBoW2 as its LCD module and mask-CNN for object extraction. Now I'm going to give you an overview of our methods. First, the input image is passed through to the Visual Bag of Words module. This module was not altered, and it uses existing standard dBoW that exists within the framework. The second module is CNN extraction and object filtering from the input image. For extracting objects from a scene, we have used mask-CNN. It was trained on the Microsoft Cocoa dataset using ResNet 50 as its backbone, and object labels were used to remove any moving objects, such as a person and car, and any objects that are too large, such as a big table which overlaps other objects. We have excluded moving objects because it helps to eliminate accidental loop closing on moving objects. And we also found that static objects provide more stable point of interest. We've also selected a limited number of largest objects, as it helps to cope better when repetitive objects are present in the scene. The third module is Semantic and Spatial Matching module. Spatial information, such as distances between each pair of objects, gets transferred into a matrix, and periodically it gets assigned to a database to be used as references for matching. Then the object distances gets normalized, as it makes the object labels to align better regardless of viewpoints or scale, and it assists with matching their correct nearest neighbor. Normalizing object distances also allow label matching process to become more robust, as it can account for detection errors such as wrong or missing labels that were propagated from the CNN extraction process. Normalized label distance matching is processed on single-dimensional elements. For object location matching, we needed a two-dimensional matching algorithm. Euclidean distance is the most common way to measure similarity between two-dimensional elements. However, it doesn't take spatial relations between all elements into account. Therefore, we used Hausdorff distance, which can compute the spatial relations between all objects and vector. Since SLAM uses a continuous stream of images, adjacent images in the sequence look very similar to each other. So we had to adjust by using a temporal similarity equation proposed by Zhang et al. However, the original equation was to penalize images that were further apart. Therefore, we have inversed the function and negated the beta to penalize images that were close by. Then we combined it with the Hausdorff distance measurement to create a Hausdorff distance with temporal similarity constraints. The last module in our method is ensemble-based loop closure candidate prediction. The information from CNN extracted objects, such as matched labels, Hausdorff distance with temporal constraints, and normalized label distances, were concatenated with the Visual Bag of Words similarity score. Then we used ensemble-based random forest loop closure predictor with the base learner function of H and an ensemble function F with a collection of base learners. We have chosen random forest because it's fast, robust, and less prone to overfitting compared to other classical algorithms such as SVM decision tree. And when the training set is small, random forest often outperforms neural nets, which requires a large amount of data to attain high accuracy. Now moving on to experiments. All our experiments were performed on a PC with Intel i9 and GTX 1080 GPU. For our experiments, we have used two public datasets from TUM, and 3 of our own datasets with varying trajectories and objects. We have measured feature importance to show the extent of symbiosis that exists between CNN-extracted objects and visual bag of word features. And the result shows the top 2 input features that influence the loop closure predictions are normalized distances from CNN-extracted objects and visual bag of word score from visual bag of word features. With combined percentage of 58%, we can see the 2 input features provide major influence over loop closure prediction. We have also performed ablation study to measure the difference between using both CNN-extracted objects and visual bag of word scores against using one feature set at a time. And the result shows that using both feature set outperforms using a single feature set at a time, with over 5.6% improvement in precision and 8.3% improvement in recall. Our SymbioLCD was benchmarked against well-known machine learning algorithms, including 3 SVM with linear, polynomial, and Gaussian kernel, decision tree, and densely connected neural net with 4 layers. Further to that, we have used autorank to analyze performance, which determines the difference in central tendency with independent paired samples to compare the mean performance of each algorithm. The result shows the SymbioLCD performed best compared to other machine learning algorithms in both precision and recall metric on all datasets. Lastly, our loop closure candidate prediction was benchmarked against state-of-the-art including OrbSlam2 and DynaSlam. They were chosen because they all share the same visual bag of word algorithm and keyframe insertion algorithm, making them an ideal baseline for this evaluation. For this evaluation, keyframe number was recorded to benchmark when loop closure candidates were found. And the result shows SymbioLCD has consistently found loop closure candidates earlier than OrbSlam2 by an average of 4.5%, and then DynaSlam by an average of 5.6% in all evaluated datasets. The result from this evaluation emphasizes that having a semantic and spatial information contributes to early detection of loop closure candidates compared to state-of-the-art, which relies on visual bag of words alone. We presented our novel SymbioLCD with ensemble-based loop closure detection systems that utilizes both CNN-extracted object information and visual bag of word features. We show that there is a strong symbiosis between CNN-extracted objects and visual bag of word features in SymbioLCD's decision-making process. It also outperformed other machine learning algorithms in both precision and recall evaluation, and finally, having semantic and spatial information contributed to early detection of loop closure candidates compared to other state-of-the-art SLAM systems. There's still a few limitations to our proposed work. It requires multiple static objects in a scene to work properly, and our loop closure candidates are not yet fully fused into backend graph optimization and bundle adjustment. As a future research, we aim to extend it to work with both static and dynamic objects. This is the end of our presentation, and thank you for listening.